Water is pretty cool, so I tried simulating it. I started with doing some research and looking at papers where I only understood about half the words.
What is upside down triangle squared?
After a few rabbit holes of Wikipedia articles and Stack Exchange posts, I was ready to start coding. So here's a ball, here's a few, and now they fall, and now they bounce off the walls. Great. Now we just need them to behave like a fluid. But how do fluids actually move? Or at least, how can we make little balls move like a fluid? The principle behind moving these balls is actually pretty simple. Essentially, it boils down to don't let the balls get too close, but don't let them get too far away either. To actually code this though, we need to know the density at each particle. So I've got a grid of balls here, which I've just frozen for now, and now we can try getting the density at the middle ball. We could just add up all the masses of the balls in some radius, which for now, the masses are all just set to 1, and divide it by the area of that circle. But we can do better. We care more about the balls closer to this middle ball than the balls further from it, so we can loop through each ball in some radius and apply some function to the distance of that ball to this one. Then we can get a weight that controls how much the other ball affects this ball's calculations. So let's take a look at some functions. So I have this function here where the x-axis represents the distance between the two balls, and the y-axis is how much the balls affect each other. Now this is what it would look like if we just added up the masses of every ball in some radius, which I've defined as r, and once again this x represents the distance between the two balls. For density, we need to divide by the area that we look in, which also makes it so that the area under this graph between 0 and our radius stays the same. Now since we're only looking at one dimension here, with the distance, we only have to divide by r. We'll divide by r again for every dimension we add, so in our two-dimensional simulation we would divide by r squared. Now let's look at a function that will prioritize closer values. This one is nice, as when distance is used, it's squared. Because of how we calculate distance, this allows us to skip a costly square root, which makes things a bit faster. Anyway, here's what it looks like, and we have to divide by r to the power of 7 in order to keep the area under the function the same no matter what the r value is. Again, in our simulation it would be r to the power of 8 since we're in 2D. Okay, so I've coded that up now, and by the way, I'm using the processing programming language, which is basically Java. And now we can test if it works. So here's a grid again, and let's choose a ball in the middle to get the density at that point. And if this works right, we should be able to change the radius that we're looking at and get the same density value. And it looks like it's staying mostly the same, so everything seems to be working fine. We can just repeat this process for every particle, every frame to get the density at every particle. Now that we have the density, we need to do something with it. And to do that, I'll need to introduce this funny looking equation. Now this might look a bit complicated, so I'll explain every part, and don't worry if you don't recognize some of the symbols, I'll explain them all later. The first part is simply how much the velocity of a particle changes through time. This is also known as acceleration, so I'll just replace it with that for simplicity. The next three things are different things that can accelerate a particle. This first one is how the particle changes due to differences in pressure, which is where the densities we just calculated comes into play. The next one is viscosity, which is like friction but for fluids and controls how quickly a fluid flows. And this last one is simply every other force, such as gravity or collisions with solids. So let's find all of these. We've already kind of done the last one with gravity and collisions on the sides, so I'll move on to the first one, which is pressure. Breaking down this first term, we can see that the density that we just calculated is right here. Now you'll usually see this as the Greek character rho, but since that looks a bit too much like p, which we're going to use for something else, I'll just replace it with a d. Now here's this upside down triangle. We'll hold off on it for a bit longer and look at the p variable. This represents pressure, which we'll calculate based off the density using this equation. We'll start by dividing the density at each particle by this variable, which is just a target density, and it's a value that we'll just have to play around with to find a good one. This is all raised to the power of 7, then subtracted by 1. and then it's all multiplied by K, which is some coefficient that determines how stiff our fluid will act. Technically, liquids are almost incompressible, so this value should be close to 1, but a very high value for this causes the simulation to become unstable, so we'll also have to play around with this value. Alright, so now let's talk about this upside down triangle, and what it actually means. Well, luckily, this paper has a definition right here, so it'll be real simple. The upside down triangle placed in front of some property of a particle, represented by A here, is simply the density at that particle multiplied by the sum of the results from a loop, where we go through every other particle and multiply the mass of the other particle with this thing here, and oh, darn. It looks like the definition for this upside down triangle includes an upside down triangle, so we actually have to figure out what this upside down triangle means. So the name for this upside down triangle is the gradient operator. Basically, it returns what's called the gradient vector at some point of the function in front of it. You can think of this as a bunch of arrows pointing to where the value of some function changes the most. So for example, here's the particle we were just looking at, and I'm going to apply our function to the surrounding area. At black, the function returns 0, and at white, the function returns 1. The gradient field looks a bit like this. There's a bit of a problem with this though. If you look near our particle, the gradient vectors get smaller, which is the opposite of what we want. Closer particles should move away faster. So I'm going to change our function to this one, which looks like this on a graph, and its gradient field looks like this. So let's try to get the gradient vector at, say, this point. We can see that it looks something like this, but how do we actually calculate it? Well, since this is a vector, there's two components, so let's start by just calculating each component separately. We can solve for the x component by moving this point a tiny bit in the x direction and seeing how much the result of the function changes when we do that. Similarly, we can find the y component by doing the exact same thing, just on the y-axis. Now when we put these two components together, we get our gradient vector. Now there is a mathematically precise way of figuring out each component of this vector. It's called partial differentiation, and I won't get into the details, but we can get this expression for the gradient vector of our function. So putting that into code, it looks like this. Well, this isn't looking much like a fluid, so let's add some more particles. Alright, so right now our code kind of sucks. Every frame, for every particle, we're looking at every other particle to see if it's in the radius. That's a lot of checks. In fact, for a 20 by 20 grid of 400 particles, that's 160,000 checks my poor computer has to do every frame. So let's try cutting that number down. We're going to start by dividing our simulation into a grid with a bunch of squares, where the side length of a square is the length of our radius. Now we can see that no matter where a particle is, the radius is completely surrounded by the 3 by 3 grid area around it. That means that any particle that can possibly be in the radius is also in this 3 by 3 area. So if we only look at the particles in this 3 by 3 area, it'll speed things up by a lot. So here's how we can do that. Every frame we need to give the particle a number, based on what grid tile it is in. Now we could just start from the top left tile and number the tiles in order, but we want our simulation to end up being infinite, so we don't know how far it'll go in any direction. So instead, let's do this. We'll take the position of a particle and convert it to a grid position, so how many grids in the x and y direction from the origin that particle is. We'll take the x-coordinate of this grid position and multiply it by a large prime number. This one here should do the trick. We'll do the same with the y-coordinate, but with a different prime number. Now the result of this is completely unique, so no other set of coordinates will give the same result. Now these numbers are pretty big, and we'll never need more of these numbers than the number of particles we have on the screen, so let's modulo all of these numbers by the number of particles. And we'll call the result of this the hash. Keeping a loose track of the number of calculations we've had to do, it's at about 400 right now, one for each particle. The next step is to sort the particles based on the number we just got. We'll use a nice and fast sorting algorithm called merge sort, which just takes about 3,458 comparisons for the 400 particles we have, which brings our total to 3,858 calculations. So far, much better than the 160,000. Finally, we'll go through our particles list again from top to bottom. Every time there's a change in the hash number, we'll go to another array at the index of that hash number, and we'll store the index in the particle array that we found the hash number at. This is why it was so important to modulo the hashes by the number of particles, otherwise the other array that we've just created would get very large. We'll add another 400 calculations to our total count, making it 4,258. Now for each particle, we can simply look in each grid tile around the particle, get the hash at that tile, use that to get the value in the other array, which will be the index of where all the particles in that tile are located in our particles array. Now we can simply do our calculations on that particle if it's in the radius, then go forwards and repeat the process until the hash number changes. Repeat all that for every tile around the particle we're looking at, every frame. The number of calculations in this step depends on how close the particles are together, but if we assume there are 40 particles in the 3x3 area around each particle, we're adding about 16,000 calculations. So our total ends up being about 20,258 calculations. Much better than our 160,000. And after a bit of multi-threading for even faster improvements, our simulation is looking like this. Very cool. It's already looking a bit like a fluid. Well, it was looking like a fluid. Okay, so I think I know what might be happening. Right now, when we move the balls, there are three values: position, velocity, and acceleration. Every frame, we simply take the accelerations applied to the ball, add that multiplied by the seconds per frame to the velocity of the balls, then add the velocity multiplied by the seconds per frame to the position. This is called explicit Euler method. Theoretically, it works fine if the amount of seconds per frame is infinitely small, like in real life. Unfortunately, this isn't real life, and my computer isn't infinitely fast. To show why this is an issue, let's look at a simpler scenario. This is a gravity simulation. Here's the Earth with its acceleration and initial velocity, and here's the Sun. What we want our simulation to look like is something like this. But let's try using the explicit Euler method for a frame, and I'm going to make the time interval really large just to exaggerate. Okay, so let's add our acceleration to our velocity, and now let's move the Earth by the velocity. And here we can see we've already moved off the path we want. If we repeat this for the next path, we can see that the Earth gets more and more off the correct trajectory. When the time step is lower, the effect is much less, but still over time you can see the effects. One way to fix this is a technique called Runge-Kutta fourth order integration, also known as Runge-Kutta 4. Basically, it works a bit like this. We'll start by taking the velocity from the last frame and applying our acceleration to it, just like in explicit Euler. Then, we'll store the acceleration and move Earth halfway along the velocity we just calculated. Now we calculate the acceleration again, this time at the midway position, and store it. Once again, apply it to the velocity. Now, move Earth and the new velocity we just calculated back to its initial position and apply half of that velocity. Find the next velocity from there and move the velocity and the Earth back to the start again, and finally move along the entirety of this velocity and find the final velocity, storing all of the accelerations along the way. Now take the average of all these accelerations, weighing the two middle ones 2 times more than the others, and apply it to the initial velocity, and now we have a more accurate velocity. Finally, let's move Earth along this velocity, and there we go. Still off, but much better. So after coding that up, this is what it looks like. And nothing seems to be breaking, so Runge-Kutta must be working perfectly, except it still hasn't solved the problem. Okay, I have no idea why this might be happening right now, so I'm going to employ a very sophisticated and complicated tactic called pretending it doesn't exist and hoping it solves itself. So now that our fluid is working perfectly bug-free, with no issues whatsoever, it's time to look at the final term in our formula: viscosity. Viscosity is also something that boils down to something quite simple. Move a particle in the general direction that the other particles are going. To actually figure that out, however, it's also a bit more complicated. Once again, let's go through each variable. This first one, v, is just a coefficient for viscosity, which is another thing we'll have to play around with. This next one, once again, has our funny upside down triangle symbol. This time, it's also squared. Once again, one of our papers has a definition for this, and once again, it has our symbol inside that definition. This symbol squared is called the Laplacian operator, and it's calculated by taking our gradient vector at some point and dotting that with itself. We don't have to worry about that though, because we won't be using the same function here as we're using for our density. We're going to use this complicated looking function just for viscosity. This ends up working in our favor though, since the Laplacian of this function ends up being this really nice function. So once again, it's a matter of translating math into code, and after that, our fluid simulation is looking pretty good. The next thing I wanted to try is a method from one of our papers that makes slight tweaks to how we calculate pressure and fixes some small clustering issues. We'll start by creating two new properties to our particle, near density and near pressure. Near density is easy. We'll just calculate it exactly like we calculated density before. We'll also change our density calculation so that it uses this function here. For near pressure, since we want it to only push away, we'll just multiply the near density by some coefficient and add this near pressure to wherever we use normal pressure. And it looks like this. It's looking pretty good, and it seems our exploding problem has also fixed itself, so my tactic has worked. Anyway, now I've coded up some simple controls so that we can play around with and interact with the simulation much more. I've also added some rudimentary and buggy solids code, but that deserves to be explained in another video. Alright, so I'm pretty happy with where this fluid simulation is for now, but I want to add some improvements to it later. I'm thinking of potentially rewriting it in another language, adding 3D, more performance improvements, better solids, maybe even soft bodies, and possibly even more down the line. So if you'd like to see that, let me know by pressing any number of the buttons below this video. But otherwise, that's it for now.